The world of AI is evolving rapidly, and occasionally, a breakthrough comes along that changes how we view these systems and their capabilities. One such innovation is something called BARAR. While the name might sound sophisticated, the concept is remarkably straightforward. It's about enabling AI models to teach themselves more effectively without relying heavily on vast amounts of human-generated data. As AI models become increasingly advanced, their demand for high-quality data continues to grow. Whether it's solving intricate math problems, writing complex code, or grasping basic logic, these models heavily rely on meticulously curated datasets crafted by humans. However, as tasks become more challenging, creating these datasets becomes both time-intensive and costly. Imagine a teacher needing to handwrite every single textbook for their class. It's a similar scenario. This is where self-improvement methods come into play. These approaches aim to minimize human intervention by enabling AI models to enhance themselves through analyzing their own outputs. Here's how it works. Self-improvement operates in cycles. An AI model generates responses, evaluates and selects the best ones based on specific criteria, and then uses those examples to refine its capabilities further. Think of it as a feedback loop, where the model continuously improves by reassessing its own outputs. This idea isn't entirely new. Methods like STaR and RFT have been working on similar concepts for a while. These approaches have demonstrated that achieving strong results without massive datasets is indeed possible. However, they've also encountered significant challenges. After a few cycles of self-training, these systems often hit a wall. Their performance stagnates, and no matter how much additional data or computational power is applied, further improvements seem out of reach. The team behind BARAR set out to uncover the reasons behind this limitation. Researchers have discovered that two critical factors play a pivotal role in determining how effectively a model can enhance itself: exploration and exploitation. These terms might seem technical, but they're actually quite simple. Exploration is all about the model generating a variety of accurate and diverse responses. It ensures creativity and avoids repetitive or overly specific answers. On the other hand, exploitation involves leveraging a reward system to identify the most effective responses and prioritize them. The key challenge lies in achieving the perfect balance. If a model emphasizes exploration too much, it risks generating irrelevant or incorrect outputs. On the other hand, focusing excessively on exploitation can make the model overly conservative, repeating familiar patterns without learning anything new. This is where BARAR comes in, a framework specifically designed to monitor and dynamically adjust these two aspects during the training process. Unlike traditional methods that rely on fixed settings, BARAR adapts in real time. It fine-tunes parameters such as sampling temperature and reward thresholds to optimize performance at every stage. Sampling temperature controls how creative the model's responses are. Lower temperatures result in more focused answers, while higher temperatures promote greater diversity. Reward thresholds determine how strict the system is in accepting responses. Together, these settings influence the model's behavior, and BARAR ensures they are always aligned to produce the best outcomes. To assess how well this balance is working, BARAR introduces a metric called the balance score. This evaluates both the quantity and quality of the model's outputs. The goal is to ensure the model generates a sufficient number of high-quality responses for effective learning. For instance, if the system selects 64 responses but only 16 are correct, the imbalance will be reflected in the balance score. This score tracks the discrepancy and helps BARAR make informed adjustments to keep the training process on course. The researchers evaluated BARAR on various tasks, ranging from mathematical problem-solving to common-sense reasoning. For the math tasks, they used datasets like Math and GM8, training models such as Mistal 7b. These tasks are easy to verify since the correctness of the answers is clear. Either they're right or they're not. Coding challenges were assessed using the APPS dataset, while common-sense reasoning was tested with the ARC Challenge dataset, which includes multiple-choice science questions. Across all tests, BARAR significantly outperformed other self-improvement methods. In the GSM-8K dataset, which focuses on math reasoning, BARAR achieved a pass rate of 53.8%. surpassing the 46.8% of online RFT and 46.3% of RSTEAM. For the math dataset, BEAR scored 27.8%, a solid improvement over the 23.2% achieved by online RFT. Even in coding tasks where models typically face difficulties, BEAR reached 19.6% accuracy on Passé 1, outperforming all competing methods. These numbers might not appear significant at first, but in the realm of AI, even small percentage changes can signify a major leap forward. What's even more remarkable is how Barar maintains steady progress through multiple iterations. Traditional methods often hit a plateau after 3 to 5 training cycles, yet Barar continues to push forward. This sustained advancement is directly due to its dynamic adjustments. For instance, during the initial stages of training on the math dataset, Barar set the sampling temperature to 0.5 to prioritize accuracy. As the model improved, the temperature was gradually increased to 1.1, promoting more diverse outputs. Similarly, the reward threshold started high to ensure strict quality control, but was slightly relaxed later to provide more flexibility. These adjustments aren't random. They're carefully fine-tuned to optimize the balance score. By consistently monitoring both exploration and exploitation, Barar ensures the model stays on course. This dynamic approach marks a significant improvement over static methods like STaR, which resets the model after each iteration, or iterative RFT, which doesn't adjust its settings throughout training. The experiments also emphasize the importance of incorporating additional reward models, particularly for mathematical reasoning. Combining final answer matching with a process reward model (PRM) resulted in better performance. The PRM evaluates the quality of each step in the solution, offering more detailed feedback than simple binary rewards. This finer-grained feedback helps maintain the model's exploratory capabilities, preventing it from falling into repetitive patterns. One of the most notable discoveries was how exploration evolves during training. Early in the process, the model's diversity metric rises, indicating it generates a broader range of solutions. However, without proper incentives, this diversity tends to decline over time. To address this, Barar promotes exploration in later stages, ensuring the model continues to learn new things. Meanwhile, exploitation metrics, such as the best of K accuracy, show consistent improvement, suggesting that the reward system is effectively selecting high-quality responses. The researchers also tested Barar on more powerful models, like Llama 3.18b. Despite these larger models being inherently more capable, Barar still provided significant improvements. For instance, it reached an accuracy of 61.6% on GSM-8K and 29.2% on math. Barar outperforms traditional methods by a significant margin. Its scalability makes it an adaptable tool for various applications, ranging from education and programming to general problem-solving. What truly sets Barar apart is its ability to break down the process of self-improvement. Unlike previous methods, which treated this as a black box, where you would simply run the model through a few cycles and hope for the best, Barar provides a clear framework that allows us to understand what's happening at each step. By quantifying exploration and exploitation, it offers insights into why certain approaches succeed or fail. This transparency is invaluable for researchers and practitioners striving to push the limits of AI capabilities. The potential applications are vast. Imagine applying this framework to robotics, where machines must adapt to complex real-world environments, or in creative fields like writing and design, where generating diverse, high-quality outputs is essential. Barar's ability to balance creativity with precision makes it an ideal solution for these challenges. The future of Barar looks incredibly promising. Thanks for watching! If you enjoyed the video, don't forget to like and subscribe. See you in the next part.